It's Paul with a Math156 script designed to illustrate lots of situations where the chi-square distribution is an appropriate model for data. This topic is introduced in section 3.4.2 in the textbook, which you should certainly read beforehand, and you might want to go on ahead and read section 3.5 also. So what I want to show you is lots of situations where we know the underlying probability distribution that gives rise to a set of samples, and we end up with a chi-square distribution when we follow the standard recipe of take the difference between the expected and observed values in each cell, square it, divide by the expected value, and then sum up all the results. That's the standard chi-squared recipe. I'm going to use an expected value of 156 throughout this file. You can make that larger or smaller if you want to play around with this, but it helps to have exp be an even integer for certain distributions because I'm going to be dividing it by 2. I'm also going to be collecting and analyzing 10,000 samples. If you're running this on a slow computer, you might want to make capital N a little bit smaller. Okay, let's get going. Simplest case. The observations come from a normal distribution, and both the mean and variance of this distribution are equal to the value I'm calling exp. In that case, what I get when I divide through by exp is a variable that arises as an example of the standard normal distribution. So let's generate samples from the normal distribution, or let's look at the density function for the normal distribution with a mean of exp and a standard deviation of the square root of exp, that is, a variance of exp. So there it is, nice continuous distribution, and now we can generate lots of samples for it. 10,000 times we will save a value, and what we will do with the sample is we will subtract off the expected value, we will square the result, and then we will divide by the expected value. So here's a histogram of those results, and here is a plot of the chi-squared density function for 1 degree of freedom. Perfect match because this is how the chi-squared distribution with 1 degree of freedom is defined. It results from squaring random variables drawn from a standard normal distribution. It has a mean of 1 and a variance of 2, and sure enough, the mean and variance of the samples we generate are close to that. Now let's try something a little bit different. Our random variables have a Poisson distribution where the parameter is the number exp, and the interesting thing about the Poisson distribution is that the mean and variance are both equal to its parameter. So again, we've created a situation where the mean and variance equal exp. It's only worth plotting this between 100 and 200 for exp equal to 156. So here is a plot of the Poisson density function. This is a discrete distribution, but doing plot with type equals h gives us a very, very nice looking histogram that you can compare with a continuous distribution. And in fact, if I overlay the density function for the normal distribution, there's a nearly perfect matchup. Again, we're going to do the same thing. We're going to generate lots and lots of samples, but with each of these samples that we get from the rPos function, we're going to subtract off the expected value, square the result, and then divide by the expected value. So this is the chi-squared recipe: observed minus expected quantity squared divided by expected. And here's a histogram of the results. Maybe this chi-squared distribution is starting to look familiar now. There's an overlay of the density function for the chi-squared distribution. And again, the mean is close to 1, the variance is close to 2. If you repeat this with a smaller value of exp, the fit will be less good, though. Let's try again with a binomial distribution. This time I'm going to make a binomial distribution where the number of trials is 100 times the value exp, but the probability of success is only 1%. So the expected number of successes is exp. The variance, as you know, is a little bit smaller. It's only about 99% as large. And when you look at that, well, the distribution is nearly Poisson, but in this case, you really can't tell that it differs much from a normal distribution. There's an overlay of the normal distribution density function for the same mean and same variance. Let's generate some samples again. Exactly the same recipe. Get the observation by using our binom, subtract off the expected value, square, divide by the expected value, make a histogram, and that's what the histogram looks like, and it agrees, again, nearly perfectly with the density function for the chi-squared distribution. The mean and the variance are close to 1 and 2. In this particular case, by the way, if you're changing the numbers, exp divided by p has to be an integer, because the number of trials in a binomial distribution has to be an integer. Here's something more exotic. A gamma distribution where r is equal to exp and the rate is 1. That means there's an e to the minus x in the density function. This is actually the result of adding together a very large number of exponentially distributed random variables. And here is what the density function looks like. You say, that looks mighty normal to me. And sure enough, if you overlay a normal distribution with the same mean and same variance, it's kind of hard to spot the difference. We generate some samples again. Exactly the same way. Plot a histogram of the samples, and sure enough, it matches. So the message I'm trying to get across here is there are lots of ways of generating samples, and they all have the property that if you take observed minus expected squared over expected, you will get something that has very nearly a chi-squared distribution. Here's one last example, the so-called negative binomial distribution. Suppose you take a fair coin, flip it, and count how many flips you have to do until you get exp over 2 heads. Clearly, the expected number of times you're going to have to flip it is exp, in which case you get equal numbers of tails and heads. This function is built into R, but it just counts the number of tails, so we have to be careful in using it. X is going to be the total number of flips, including the exp over 2 heads. And what we're looking for is a number of tails that's equal to x minus 1/2 of exp. So here's a plot of the density function for the negative binomial distribution. Again, it's a pretty good match for the density function for a normal distribution with the same expectation, same variance. Generate samples in exactly the same way. There's the histogram. There is the chi-squared density function overlaid. There are the mean and variance, again close to 1 and 2. Now a topic that really puzzled me, and I explored this in the math notes in the previous week. Why do we sum over all the cells in the table? And the answer is because that gives us something with the right mean and variance. In simple cases, we're actually summing up things that are proportional, but it's the sum that matches the chi-squared distribution perfectly. So let's have an expected number of counts of 100 in the first cell, 200 in the second cell. Suppose I have 120 observed counts in the first cell, then the number of counts in the second cell, of course, has to be what's left over, in this case 180. So there's our contribution from the first cell, it's 4. If we use the second cell, we get 2. And if we sum them, which is what one does for a standard chi-squared test, we get 6. Now let's keep track of what happens with these sums for the individual cells. I'll save the value in the first cell in values 1, the value from the second cell in values 2, the values in the first two cells summed in values sum, and finally a rescaled version of the values in the second cell. I'm going to assume a binomial distribution, 300 trials, 1/3 probability of success. That should give us an expected number of successes equal to 100, an expected number of successes of failures, which show up in the second cell, equal to 200. So I generate my observation by using the R binom function with 300 total trials, probability 1/3 of success. I calculate the number of failures. I then save the chi-squared value from the first cell only, the value from the second cell only, the sum of those two contributions, and a rescaled value from the second cell where I have multiplied by 3, multiplied by 1 plus the expected number of failures over the expected number of successes. And now let's look at various histograms. This is from the first cell only. You say, hey, that looks chi-squared to me, but not quite. You can see that most of the bars lie below the curve. This histogram is squished to the left. The mean is too small, the variance is too small. If we look at the value in the second cell, we see the same general phenomenon. Again, the mean and variance are much too small. If I add the two together, we've got it just right. There's another histogram, and that matches up beautifully with the chi-squared distribution. We can achieve the same effect by taking the value in either of the cells and rescaling it appropriately, with the rescaling factor chosen so that the mean comes out close to 1, the variance comes out close to 2. There's our nice matchup. There's confirmation that we rescaled so the mean and variance were correct. So the moral of this is you don't really have to sum over the entire table. If you're willing to rescale, you can get a chi-squared distribution from just one of the observations. But if the data are from an unknown source, adding the contributions from all the cells together is a much more sensible thing to do than rescaling. Now let's try with 2 degrees of freedom. So this is going to give us a 3-way table, and I'm going to set up a table where the expected number of counts is 100 for cell 1, 200 for cell 2, 300 for cell 3. I'm going to do this 10,000 times, and I can do this by using the built-in multinomial distribution in R. I say n equals 600, and the probabilities for the 3 cells are 1/6, 2/6, and 3/6 in succession. When I use R multinome, I have to tell it I want 600 total samples, but I can specify the relative probabilities without bothering to rescale. So I just make a vector out of the expected number in cells 1, 2, and 3, and that gets rescaled automatically by dividing by the sum. So here's some observations. If you look down at the bottom, you'll see I got 3 numbers, one of them close to 100, another close to 200, another close to 300, and the sum guaranteed to be 600. To do a chi-squared test, I have to sum over all 3 cells, as is done here. If I use just the first two cells, gosh, if you know what's in the first two cells, you can calculate what's in the third cell, but it's not going to work. Why? The result's now chi-squared with 2 degrees of freedom. There's a histogram for it. There's the chi-squared distribution with 2 degrees of freedom overlaid. Perfect fit. Incidentally, this distribution is exactly the same as an exponential distribution. The blue curve sits right on top of the red curve. And in this case, the mean for the chi-squared distribution is 2. The variance is 4. And for my samples, I get fairly close results. If I use just the first two cells, the histogram looks fine, but again, it lies to the left of and under the chi-squared curve. That means we just didn't scale up enough. The values are systematically too small. And sure enough, if you look at the mean and variance, they're significantly less than 2 and 4. It's the contribution from the third cell that fixes that. So now you've got an idea of why you sum over all the cells in the table, and this script is finished.